supply chain. The FRIETS project is now in its final months of implementation, and it's been a very productive journey. From the start, our aim was clear: to enhance sustainability along the dairy value chain by combining scientific research with practical solutions for stakeholders. Throughout the project, we have worked closely with growers, researchers, and stakeholders in order to co-develop solutions that are not only technically effective but also aligned with real-world needs. Today, we will go through the key pillars of the FRIETS project, our innovative approach to pre- and post-harvest practices, the technologies we're exploring to enhance freshness, reduce waste, and add value in our berries. And finally, our integrated sustainability assessment framework, which ensures that our solutions are not only effective but also responsible. The outcomes we have achieved so far reflect the collaborative effort of diverse and dedicated consultants. We are proud of the work completed and excited to share today with you some of the key results of our project. Thank you very much for your attention, and I look forward to the presentation ahead. Thank you.
So, the first presenter is Mr. Panagiotis Frantsis from Agricultural University of Athens, and he's going to present us the pre-harvest innovations enhancing crop yield and quality of berry production.
Hello everyone. Can you hear me? So let's start with the presentation. First of all, my presentation is been divided into 4 sections: the introduction, the aim of the study, the methodology, and the results is a part of our first study in the FRIETS project, and the next section is a part of our second trial, which is currently underway. So let's start with the introduction. First of all, a brief introduction and description of what precision farming is. Precision farming is a method that relies on data and uses technology, sensors like GPS, AI, in order to achieve efficiency, productivity, and sustainability by using optimization of fertilizer, water, and pesticides. The technology are commonly used in precision farming. In precision farming, it's a sensor like soil moisture, nutrient and the canopy sensors, drones and AI imaging that detects health, stressing growth development, and automated irrigation and fertilization by using the variable rate application. So here are some benefits of precision farming for berries. First of all, the optimization of nutrients and water achieves the improvement of berry size and flavor. In addition, the resource efficiency of water, fertilizers, and pesticides lowers the cost of the farmer in order to acquire them, and of course it reduces the environmental impact. In addition, we can early detect stress and disease by using remote sensing and AI in order to avoid the development of them. And finally, the climate resilience. We can avoid the temperature and the rainfall variability by acquiring data from sensors in our field. So here you can see raspberries production in Cyprus, where both of our trials are conducted. As you can see, Cyprus has two specific climates. The hot Mediterranean, which is located from 0 to 500 meters altitude. It's, as you can see with the red line. And the mild cold Mediterranean, which is range from 800 meters to 1,200 meters, where we have 8 growers in the region of the Mediterranean and 5 growers in the mild cold Mediterranean. So here we have some more information about the unique climate of Cyprus. As you can see from the map at your right, you can see that we have high altitude, first of all, in the center of Cyprus, and we have a unique spatial temperature variation within the 70 kilometers radius, which is quite unique. And here are the details of the two climates. As I referred before, the mainland climate, the hot Mediterranean climate, it's located from 0 to 500 meters above sea level. It has a very hot summer average of 33 Celsius degrees with maximum of 47 degrees and the minimum of 25. And the mild Mediterranean with mild summers of average of 25 Celsius degrees. And here are some climate data of 2022, when the first study of AUA in cooperation with the FRIETS Project were conducted. As you can see, we have the two diagrams of soil temperature and air temperature. The max values were reached in the beginning of August, with 28.05 in air temperature and 21.088 in soil temperature, and the minimum of -3 in the mid of March. Here we have the diagram of soil electrical conductivity, which is one of the essential parameters for the development of the plant in the specific soil. We have the maximum value in mid of June and the minimum of the mid of July. And here it's the daily precipitation diagram, where we have the maximum precipitation in the beginning of the year. So let's continue with the second section on the aim of the study and the methodology. So our first aim is to characterize 3 different cultivars. Specifically, we studied 3 varieties of raspberry, where I'm going to analyze in the next slides. And the measurements are referred to the vegetation, the number of leaves, lateral, suckers, flowers, and berries, the physiology of SPAD, NDVI, stomatal conductance, and chlorophyll fluorescence, and to identify, which is our second aim, to identify when and how to predict yield. The main goal of the study is to create a prediction model in order to predict the yield. To achieve that, we are going to investigate correlation between the vegetation indices, soil and irrigation parameters, and the meteorological data, and of course the yield. Here are some pictures of the installation of the pilot, which was conducted, as you can see, in the region of the mild Mediterranean climate. And as you can see on your left, the crops were installed into a pots, a 10-liter pots. Here are the 3 varieties I referred before in our first study. It's Kelly, Wenzi, and Imara. We have 25 replicates, 5 groups of 5 replicates each, with 10-liter pods like I referred before, and 1.8 meter row spacing, and 4 liters per hour drip irrigation. Here are some photos of the proximal area sensor that we use in our study. As you can see, the left, the handheld proximal NDVI sensor and the drone and the spun sensor. So let's see some benefits of the drones that we can use in precision farming in order to enhance some traditional, let's say, methodologies for our crops. First of all, UAVs allows the fast acquisition of data during the whole year. Of course, except if the condition allow us to do that, because we don't need rainfall at all, and we need the wind speed to be low enough in order to conduct the flight. Of course, the means for the instrument, the sensing instrument to be carried and mounted in order to achieve remote sensing imaging. And of course, the sensing instrument that I referred, it's usually cameras, RGB, PEPAL, hyperspectral, yes, with that accuracy. Now I'm going to describe some of the definitions that I have already referred in order to be further explained. First of all, we used the NDVI vegetation index, which is the most common vegetation index that we currently use in order to identify the density of green and to identify how much healthy is our plant. The range of NDVI ranges from -1 to 1. As you can see from the image, when the values range from -1 to 0, we don't have a live plant. We have maybe identify an object in the field or a completed plant. From 0 to 0.33, we have a diseased plant that requires intervention in order to restore its health. And from 0.33 to 0.66, we have a moderate healthy plant, and from 0.66 to 1, we have a very healthy plant. And also we have the spot chlorophyll index, which measures the optical density difference at two different wavelengths of 640 and 90 to 40 nanometers. It also measures the chlorophyll index of the greenness of the plant, with the difference that the scale is from minus 90.9 to 199.9. Here you can see the stomata conductance, which is the capability of the plant to open its stomata in order to absorb to absorb and conduct the photosynthesis, and the chlorophyll fluorescence, which when we have minimal fluorescence states, it means that the proteins that are associated with the chlorophyll, it's absorbs light, and when we have the maximal values, it's occurred when chlorophyll and adenocytes are excited from saturation plus light. So let's move on to the results. Here we have two diagrams about the agronomic characteristics of our three varieties. As you can see, according to the first diagram, Wenzi develops more leaves comparing to Nimara, but the laterals, the development of laterals, it's we have a higher number in Imara from Kelly, and and from the game's height, as you can see in the 12th week, at the beginning of this diagram, you can see that they have similar development of the game's height, and mostly in Kelly and Wendy. So about the flowers development, we can notice that Imara develops more flowers than what's in Imara, and the Kelly's width, it's almost starts with the same width of 1 centimeter to 1.1 centimeter. And after the 18th week, we can see that the Kelly develop larger width. So about the stomatal conductance, you can see what during the weeks of 14 until the week 18, Kelly in whole range of time range, you can see that it develops more stomatal conductance values that means that it's more capable to evaporate water. So here we have the chlorophyll index diagram and chlorophyll fluorescence. On week 15, you can see that the three varieties have lower chlorophyll index because it's the stage where the development of the fruit started. That's why it's decreasing from 90 to 50, as you can see. And simultaneously, the same occurred on the chlorophyll fluorescence. So about the yield, which is the most important parameter, let's say, you can see that in the total number of berries, Kelly produced more berries per plant. And in the same time, it produced more fruit, more weight of the fruit. But Wednesday, at our last diagram, as you can see, have more average berry weight. So let's move on to the vegetation indices. Here you can see the three of them, of these indices, the OSABI, GNDVI, and NDVI at your right. And here we conduct measurements and we calculate 5 vegetation indices in order to compare them and to identify which of these indicators can correlate with the yield in order to integrate it into our prediction model that we want to create. As you can see, on the date of November of 2022, NDVI and GNDVI showcase higher values of, sorry, of 0.76 and 0.75. So this is our first result that indicate that we can use GNDVI and NDVI for our prediction model. It's one important result to showcase that. And here we calculate the correlation between the berry number and the berry weight with these two indicators. As you can see, in our first correlation, we achieved the square curve of 0.77 between the berry number and the GNDVI. In addition, the correlation between berry weight and GNDVI has a correlation of 0.79, and the berry weight with NDVI is correlated to 0.74. So to conclude all of these results I have just presented, Kelly and Imara have higher transpiration rate and are more vigorous in overfield long production. This is our first result, as you can see from the diagrams. Also, Imara promotes vigorousness to fruit laterals, as you can see here. In the first diagram, you can see in the middle that Imara produce more laterals than the two other varieties. Kelly also puts this vigor into structure production, which is also in the diagram I have just shown. And of course, one of the most significant, let's say, results is that GNDVI and LDVI correlates very well with the yield, so we can use it to create the prediction model. And also, wedging has higher berry size and has better photosynthetic efficiency. So, in the next steps, I'm going to showcase a brief description of the trials, which is currently in progress here with the cooperation with the FRIETS. So, the second trials have to do with the strawberries and blackberries measurements. First of all, we choose the variety of strawberries, San Andreas, as you can see. When we took weekly measurements of weather conditions and soil data, we conduct two times a week yield. And in addition, we measure NDVI with proximal sensor right before and after the harvest of each week. And of course, nitrogen drainage, electrical conductivity, pH before and after the harvest. And in order to compare the proximal data that we currently acquired with the aerial data from the drones, we conducted every 21 days flights with the drone, mounted with a multispectral camera. So here you can see the installation of the plots. We have 6 groups of grow bags, including 30 plants each. So the summary is 180 plants. In the application, we use Athens with a dosage of 100 cc per 15 liters with ultra low volume sprayer. We made this application in order to promote early harvest. Our crop is also applicated with the liquid foliar fertilizer with the 500 NPK in order to support the plant growth. And it also, we use this specific application to develop better quality appearance, such as the shade. And we have medium characteristic analysis and solubility. So our second crop is the blackberries, Mary Carmen, which we use the same methodology as with the strawberry, with the weekly measurements of weather conditions. The yield is going to be conducted every week, just like the strawberries, and the final yield is going to be harvested in the end of July. We also conducted NDVI 2 times a week before and after the harvest, just like the strawberries, and soil nitrogen, electrical conductivity, pH before and after the harvest. And at the same dates, we conduct aerial flights with the drone. The application of the blackberries is the S prime at the same dosage of 100 cc per 15 liters with the ultra low volume sprayer. We have the same plots of 6 groups including 30 plants, so of 180 plants summary. We use S prime to enhance photosynthesis and to promote mostly root formation that we need. So the outcomes from all these measurements that we gathered, we will create vegetation indices that are going to be correlated with the yield as I presented. And from this higher correlation of vegetation indices, we are going to create the prediction yield map. And you can see on your right the steps in order to achieve that. The multispectral images gathered from the drone are going to be collected and to be aligned. In order to achieve that, you have to have common points in these images in order to create an alignment. From this point, you can create the dense cloud that involves all the points required. And by fusing all of these multispectral images, we can create the orthomosaics, which is one image of all multispectral images fused, and it is geo-referred, and you can see any values of the NDVI and the every vegetation index in this image. From orthomosaics, we can calculate the two chosen vegetation indices, like NDVI and DVI. Afterwards, we have to remove the ground and the soil in order to keep only the crop in our image. And after we complete the mask of the image, we keep only the crop that is going to be trained to a model in order to predict the yield of our crops. So last but not least, I would like to thank Nicolas Paranidis for his contribution, and of course to let us do our trials to his facilities. And Professor George Macanaris and Dr. Marta Balcels, and of course my co-workers Nicoletta Dara and Jeroen Papadopoulos. Thank you very much.
I have one question. Do you have an estimation, rough estimation about what are the quantities that you save in terms of water, hectare, or just a rough estimation?
According to our second trials, water, for now, no. We mostly have focused on the vegetation indices that do the greenness of the crops.
And not with the resources used
Yeah, because we are currently in progress. I believe the next month we're going to have this result according to the water.
Water, fertilizer, and the spraying.
Exactly. For now, we just start applying and calculate the specific dosage of fertilizer, and we measure the specific water dosage of the trial.
But from the first trials, do you have any results with that? As an estimation, just to have a range more or less about what we say.
The first trial has mostly the goal of the trial was to correlate the yield with the distribution.
I see.
So it's going to be a part of the second trial with the results that we have in progress. I believe during July we will have every
The review meeting is going to be important thing to mention, because this at the end is going to be the greatest output of these products.
We're going to calculate any input of the crop. The water, the fertilizer, the pesticides, we use any going to be great for the model.
Thank you, Panayotis. Thank you very much. Let me see, because I saw some questions in the chat. You put it up or not? So, our next presenter for today is Alexandra Mari from National Technical University of Athens. But they cannot see it in, let me share my screen. They cannot see it in the online participants. I think with the share screen it will work. Works. You can see that?
Perfect. Yeah.
So hello everyone, I am Alexandra Mari from NTUA and I'm going to present you the drying technologies we use for the post-harvest of the berries. So why is drying important in the food industry? Because food, the drying of the food can lead to the reducing of the moisture content of the food products, and that can lead to the extension of the shelf life and the insurance of the product safety. It's also a method essential for preserving the color, the flavor, and the nutritional value, and it's critical for the economic storage and transportation of food products. The product preservation is really important, so with drying we can maintain the quality attributes, and there are many cutting-edge drying methods that are used in the food industry. The most common is the hot air drying, which uses hot heated air to remove moisture. Spray drying, which is used for liquid food, and it's common for milk powder, coffee, and other flavorings. Freeze drying is a method where the food is frozen and then dried. Vacuum drying is performed at lower temperatures under vacuum, so it's suitable for heat-sensitive products. And microwave drying is microwave energy is used to directly remove water by heating, and osmotic dehydration is a method where the food is immersed in a hypertonic solution and the moisture is extracted. So in FRIETS, we worked on 3 drying methods. We worked on osmotic dehydration, which, as I mentioned, is a process where the water is removed from the food by immersing it in a hypertonic solution, which is usually sugar or salt. And with the difference in the osmotic pressure, the moisture diffuses from the food and solids enter the food. So it's a very common method and it's suitable for sensitive products. The other method is freeze drying, also known as lyophilization, where the food product is first frozen and then the water is removed by sublimination. It's also suitable for sensitive food as the temperature is really low and the food product is not affected. The third method we tried was microwave vacuum drying. It is a rapid dehydration method that uses microwave energy, which means heat, in order to evaporate water. The water diffuses from the food. However, it is not suitable for all food products as they cannot, some food can degrade in high temperatures. So to compare the 3 methods, osmotic dehydration is really good it's a low energy consumption method. It can maintain the color, flavor, and nutritional quality of the food. It works at reduced drying temperature However, it requires long time. Solids may enter the food, altering the structure and the taste. And there is a problem in reusable solutions. Freeze drying is exceptional for sensitive products, as no heat is used. It can retain the nutrition, the color, and the flavor of the food. However, it has a high energy consumption and a high cost, as it requires also specialized equipment. Microwave drying is a rapid drying method, which reduces the drying time significantly. However, it can lead to uneven drying and is not suitable for all food products. The industrial scale challenges for the drying methods is, first of all, the process control and consistency, as food products are not uniform and there are variables like size and moisture that differ from fruit. There has to be methods for automation of the process. Also, the on energy and resource efficiency is really important, as there is high energy demand, and also the resources need to be reutilized. Of course, the equipment is also a challenge, because the industrial scale equipment is in high cost. So some solution is that there needs to be an advanced automation system with real-time monitoring and data for each food product. There needs to be energy recovery system in order to utilize again the energy sources. Also, the combination of drying methods can lead to good results while enhancing the product quality. Also, some pre-treatments like blanching can help prepare the food products for drying. Also, the equipment and the staff may be suitable for these procedures. So our project, our aim was to develop novel processed berries with superior quality and extended shelf life, and one of the processes we used were these three methods of drying I mentioned. So as we have mentioned, we were partners from Europe, from both universities and companies. We worked together specifically for drying 21 secondment were implemented. It was exchanged between universities and companies, and this helped the researchers to gain real-world industry experience, and the company staff to have access to research, to academic research. And this leads to long-term partnerships. So, as I mentioned, we tested three drying methods: the osmotic dehydration, the freeze drying, and the microwave vacuum drying. We tested various conditions in pilot scale and lab scale in order to find what is better for each berry. The basic results from osmotic dehydration, we noticed that increasing the temperature during the procedure had significantly improved the water loss and solid gain. However, if we raise it to about 55 degrees, it had a serious effect on the berries. The optimum solutions were apple juice and glycerol, and the optimum time was about 6 hours. So microwave vacuum drying, we noticed that it is not suitable for berries, as the high temperature affects their quality. The blueberries, we tested it on blueberries and raspberries. The blueberries retained their shape and color. However, the raspberries were shrinkaged and their color really decreased. So also in sensory evaluations, it didn't rank high, so it was a method that is not suitable for berries. On the other hand, freeze drying had really promising results, as it increased the concentration of phenolics, flavonoids, anthocyanins, and also we tested the combination of osmotic dehydration with freeze drying that had extremely good results in color parameters, in microbial analysis, producing nutrition-rich dried berries with extended shelf life. So here are the basic key results. we concluded that the combination that osmotic dehydration and freeze drying, either separate or in combination, are the best option for the berries we were testing. So why did we want to find solutions for all this? For berries, it's because they are a fruit, they are really sensitive fruit with a high nutritional value, and they are quite expensive, but they have a short shelf life. So it is really challenging to find ways to extend their shelf life. Our next steps are to find ways to put them from lab to market, because they can be really good healthy snacks, additives to food products, and shelf-stable products. So in the future, of course, more optimization is needed for the industrial berry drying. Also, with other methods, we can find out ways to have enhancement of the nutritional value in order to create high-value berry snacks. Of course, we need to have more sensory analysis with trained panels and to see about the shelf life. And of course, as we have also studied in our project, the life cycle assessment, the cost analysis, to be more specific about our products. So in general, the challenges in drying is that there is a need to integrate smart drying technologies based on the food product properties. So we have a method suitable for each product. Of course, the sustainability is a great challenge, as we need low energy alternatives, and we also need ways to reduce our resources. The combination of drying methods can be also a solution, as we can have a rapid drying, preserving the quality. The nutrition preservation as well is a challenge, and of course the scale up and the production of the final products. So that's all from me. If you have any questions.
Thank you, Alexandra. Now, the next presentation is from Dr. Lavinia Muresan. It is about the post-harvest innovation and edible coatings and sustainable packaging. So, Lavinia.
Thank you. Greetings to everyone. I would wait for your permission to share my screen.
Yes, I cannot see any sign. Can you try again?
To log in and log out? Yes.
Okay, to share the screen.
It's forbidden. It's written that I need to receive access.
Let me see. Δεν είναι. Για να δούμε.
I have now.
Great. Thank you, Thanos.
Thank you so much.
We can see. Thank you.
All clear, yes? Thank you so much.
Yes.
And can you hear me well?
Yes, yes.
Thank you. First of all, I would like to greet everyone from Athens. It's a pity I'm not there with you, but I am honored to be able to present today the edible coating and sustainable packaging presentation that actually has extremely importance within FRIETS project. And together with the Technical University of Athens, National Technical University of Athens, we succeed great results. And I would like to acknowledge their contribution for these results as well. To understand why post-harvest innovation and sustainable packaging matter, we need to begin with a global reality. Our planet is being overwhelmed by plastic waste. The chart on the right shows how global plastic waste production has increased in the past decades. Packaging accounts for the larger share, 100. Yes?
Lavinia, sorry for interrupting, but we lost your screen. We cannot see it now.
I'm
Are you
sorry.
still sharing?
I'm sorry. Let me.
Yes, okay, perfect.
Excuse me for these technical issues. Yes. So the chart on the right shows how global plastic waste production has skyrocketed over the past decades. Packaging accounts for the largest share, around 155.9 million tons by 2024, is the dominant contributing. Looking to the left, we see the most commonly used materials for food packaging: paper, plastic, metal, and wood. While plastic is not the most used, it possesses the most serious environmental challenge due to its resistance to degradation. And under the Plastic 2030 volunteer commitment, the goal is to reach 60% reuse, recycle, and reduction by 2030 and 100% by 2040. These are ambitious but necessary targets in the fight against plastic pollution. Sustainable packaging represents an alternative approach that integrates the three core principles of the food industry: management, quality and safety, and innovation. Moreover, these active packaging systems offer multiple functional benefits, including antioxidant and antimicrobial activity, as well as providing an effective barrier against oxygen, which is critical for shelf life extension. In addition to these protective roles, such packaging also enables the development of intelligent systems that can monitor and indicate the quality and shelf life of the food product in real time, contributing to both consumer safety and reduced food waste. Therefore, FRIETS Project came to fulfill for sustainable active packaging. And its main goal is actually focusing on optimizing the pre-harvest practices, as was presented before, and of course, using the energy efficient drying technology. Additionally, and is actually what the aim of my presentation is, explore the innovative edible coating and sustainability through life cycle analysis. So the overall aim of FRIETS is to develop these novel processed berries, strawberry, raspberry, blueberry, and blackberry, with superior quality and nutritional characteristics, as well as the intended shelf life. Therefore, composites or multi-layer edible coatings based on micro and macroalgae components, including encapsulated or non-encapsulated natural functional ingredients, were developed. In order to obtain the most effective edible coating formulation, we have optimized the coating solution by thoroughly analyzing the property of the resulting bioactive films. A comprehensive set of analyses was conducted to identify the optimal bioactive film, including biological and thermal elasticity assessment, as well as physiochemical characterization such as thickness, density, and color. One of the most critical parameters evaluated was water vapor permeability, which plays a key role in preserving food quality. All developed biofilm incorporated a previously optimized bioactive fraction, which included both free and encapsulated plant extract, namely rosemary and olive leaf extracts. Encapsulation was performed using several carriers. Among those was also maltodextrin as the carrier method to enhance stability and control release. Following the optimization process, the most suitable biofilm variants were selected for use as active packaging material for berries. And here, when we discuss about berries, we refer to all four types of strawberry, raspberry, blueberry, and blackberry. Both active films and control films without bioactive fractions were tested in order to compare and assess the specific influence of the active components. Throughout the experimental phase, coating solutions based on well-established biopolymers such as chitosan, starch, pectin, and alginate were used as control matrices. Into these biopolymer bases, various bioactive fractions were incorporated, namely rosemary and olive leaf extract, but as well as chlorella-derived protein and starch fractions. Two distinct application methods were employed: dipping, where the berries were submerged in the coating solution, and spraying, using a spray dryer nozzle to achieve a uniform coating distribution across the berry surfaces. These techniques enable a comparative evaluation of coating effectiveness and biofilm performance in real food systems. The impact of applied coatings on berries imposed a specific experimental design. Therefore, the four types of fruits were split in individual experimental batches. The coating solution was spread via both methods, spraying and immersion, on three different categories of fruits from each individual type of fruit, namely fresh, osmotic dehydrated, and freeze-dried fruits. Samples were collected after 7 and 14 days of shelf life testing, and of course compared with the control, the uncoated fruits. There were several analyses conducted. Among those were the physiochemical analysis, the pH, moisture, total soluble solids, color determination, the microbiological analysis, including the total germ number, yeast, and molds, and of course the biochemical analysis, where the antioxidant activity, total phenolic, total anthocyanins were investigated. And I will go now through all four types of fruits step by step, and among each fruit category I will discuss the three variants: the fresh, the osmotic dehydrated, and the freeze-dried berries, on which the edible coatings were applied together with the bioactive fractions. So the first fruit to be discussed are the fresh blueberries, which have been edible coated. And the impact on this fresh category of berries refers to the reduced weight loss, where we seen that edible coating significantly lowered the moisture evaporation and specifically the coating that was formulated via protein-based formulation and reduced the weight loss by 50%. The coatings as well decrease the diffusion coefficient with almost 3 steps. And here we refer specifically to the formulation of coating based on microalgae starch pectin, therefore enhance the moisture retention. Of course, the coated blueberries maintain stable brightness and color. And regarding the microbial stability, the chitosan and microalgae-based coating reduce the microbial load by 2 to 5 logarithmic colony-forming unit per gram, therefore protecting against spoilage and extending shelf life. Going further to the osmotic dehydrated blueberries that have been edible coated, we have seen that the edible coatings, especially in the combination with these dehydration methods, significantly reduce the weight loss and water diffusion, supporting the moisture preservation. The edible coatings treated blueberries maintain brightness and improve antioxidant retention, indicating enhanced visual and nutritional quality. But out of most importance is the shelf life extension, and namely the treatments combining the osmotic dehydration with the edible coatings and the addition of bioactive fraction achieved the greatest microbial load reduction, keeping blueberries safe and stable for 21 days. The third variant in terms of coated blueberries are the blueberries which have been previously subjected to the freeze drying. Adding coatings enriched with bioactive extracts such as rosemary water extract and olive leaves water extract helped maintain moisture content in this specific category of freeze-dried blueberries. But of utmost importance was the inhibition of microbial growth and oxidation, where the coatings containing rosemary and olive leaf extract effectively reduce microbial counts, with bacterial contamination in coated sample decreasing by up to 86% compared to controls, and stabilized antioxidant activity as measured via different methods like DPPH. And this achievement was actually during storage of these berries for 21 days. Going to the second fruit category, raspberries, the fresh raspberry coated had an important reduced in weight loss, up to 10% in 14 days. And specifically here, the microalgae protein coating reduced this weight loss to around 3%, showing excellent moisture barrier properties. Regarding the color preservation, the edible coatings maintain the brightness, redness, and yellowness during storage. And regarding the microbial growth inhibition, the chitosan coating reduced total microbial count from 7 to 2 logarithmic colony forming units per gram, supporting the extended shelf life. The osmotic dehydrated coated raspberries has important results in terms of moisture and diffusion control. And we have learned that the osmotic dehydrated edible coated raspberry had a reduced diffusion coefficients, but adding the bioactive fractions for this specific fruit category showed no further significant decrease. Regarding the color and total soluble sugar stability, the edible coatings help preserving the color, and the osmotic dehydrated treatment support the increase in sweetness, while the bioactive fractions stabilize the total soluble sugar and total acidity. The antioxidant loss is slowed by treatments, and the microbial growth is significantly reduced. In terms of sensory acceptance for this specific fruit category, the coatings preserved the texture and aroma, enhanced sweetness, and of course reduced the acidity, therefore leading to high consumer acceptance. The last variant, the freeze-dried coated raspberry, supported a moisture level a low moisture level, around 6 to 8%. But the alginate-based coating, and specifically those enriched with rosemary and olive leaves, significantly influence the water absorption and retention. In terms of bioactive coating, the phenolic content, this specific category of freeze-dried coated raspberry had an important increase in total phenolic compounds, which is absolutely normal considering that the freeze-drying method is actually a concentration method by removing the water and maintaining the dry weight. But of course, it supports the great stabilization over storage. In terms of antioxidant activity, this specific category retained the antioxidant activity effectively during storage, and the biofilm coating with rosemary and olive extract proved again their contribution in preserving the bioactive properties during storage. The application of alginate-based coatings reduced water absorption and water loss during storage, being minimized, especially in coated sample compared to uncoated ones. The third category, strawberries, had important results. And when we are discussing about the fresh coated strawberries, we must acknowledge that all coatings tested maintain quality and safety of strawberries over 14 days, confirming their role in prolonging freshness and shelf life. And the chitosan coating variant significantly lowered the total bacterial count, therefore proving its strong antimicrobial effect, which is anyway extremely well known from the literature that chitosan has this antimicrobial effect. The osmotic dehydrated coated strawberry reduce the weight significantly, and the variant where also the bioactive fraction were incorporated achieved the lowest weight loss, around 5.5%, and the lowest diffusion coefficient, preserving texture and juiciness. In terms of antioxidant and microbial protection, of course, the formulation where we have also the addition of bioactive fraction preserve the antioxidant capacity to the highest and drastically reduce the microbial counts. The third variant, the freeze-dried coated strawberry, brings great results in terms of moisture content, where actually compared to the fresh ones, we had a reduction of 60% of the water. Regarding the total anthocyanin content, of course, the coated samples supported a great preservation of these compounds, higher than the freeze-dried samples. In terms of color and quality, the visual appealing during storage was preserved, and thanks to the coatings and of course to the dehydration method applied prior coating. The last category, the blackberries, in terms of fresh coated fruits, The ones with covered or coated with alginate-based solution, enriched with rosemary especially, helped retain moisture and structural integrity during storage. The application of edible coatings, of course, again proved a strong contribution in maintaining the natural color of the berries, and of course also in the case of blackberries over the storage period, preventing discoloration and quality deterioration. The coatings formed a great barrier that limited microbial growth and microbial contamination, being safe over a period of 14 days. And the best storage condition was at 5 degrees during a week, where the coated blackberries demonstrated great preservation properties in terms of weight loss and sensory qualities compared to uncoated ones. The freeze-dried blackberry, coated blackberry, had a significant increase in total anthocyanin, which again is supported by the freeze-drying method, which actually is not only a dehydration method, but is also a concentration method, which actually removes the water and support a great dry matter. The antioxidant activity was, of course, highest in the freeze-dried blackberry coated with rosemary extract, representing actually an improved stability during storage compared to the control. The lyophilization preserved the phenolic compounds such as flavonoids, and of course, due to the low moisture content, the microbial growth was effectively suppressed in the freeze-dried blackberries. In terms of conclusion, we must acknowledge that edible coatings together with the bioactive fraction significantly enhanced and extend the shelf life and maintain quality of the tested berries. The microalgae based and macroalgae based coatings provide a sustainable and effective preservation method. Of course, that different pretreatments like osmotic dehydration and freeze drying prior to coating enhances preservation and nutritional retention. And in the end, I would like to mention that optimization of combined treatment reduce food waste and support sustainable industry practices. Thank you so much for your attention.
I have a question for both Alexandra and Slovenia. So, very interesting work and very promising results, but I want both of you to ask, if I was an industry, like Dorian in Malta, and I wanted you, as chemical engineers, to propose me which will be the best solution technico-economically, I mean, taking into account the price of the strawberries or other berries, and taking into account all the processes that we propose, all the combinations again, and the extent of shelf life. I mean, I don't understood the solution of the optimal solution. Had a lot of results, very positive. But I would like to tell you from your experience, for example, for strawberries, and for example, freeze drying is a very expensive process. So it would be nice to have, let's say, syntactic material taking into account economic aspects, environmental aspects, the shelf life of each berry, and the price. And this is what I wanted to ask both. Alexandra? Yes.
Lavinia, do you want to start? Do you want? Can you hear us?
Yes, may I kindly ask you to repeat the question, Alexandra, maybe in a short sentence? Thank you.
Ms. Krikida is asking if the solutions we are proposing, if they can be, if we can actually treat our berries in that way, and if it's environmental and cost friendly for an industry scale, like a company like Dorian, like.
From your results, in case, for example, of strawberries, but not technology-free microbiology results and the characteristics, but also the economic aspect, the logistics, and the shelf life, and the environmental aspect.
I can answer some things for osmotic dehydration that we have seen. So for osmotic dehydration, it is extremely important to find a way to reuse the osmotic solution, or else the environmental print and the cost is really high. So that's a challenge for the food industry. Edible for it, the whole solution. I will say it depends on the food product. I mean, for raspberries and blueberries, they are more expensive, so it has it makes sense to use these methods. Strawberries are cheaper, so maybe yes, and freeze drying and edible coating. We have tested. I'm not sure we have tested the three of them together, the osmotic, the freeze drying, and the edible coatings. But with the osmotic dehydration and the edible coating, we have seen that it is, yes. Yes. And there's a difference. So as a consumer, oh, yes.
Thank you. So it came into my mind the first question of Nicolas at the beginning of this project. And he said, could you really help me in extending at least with 1 or 2 days the shelf life of my berries? If yes, I'm the happiest man on earth. And these results actually came as a validation that using these dehydration technologies, and I would like also to refer to freeze drying, comparing in comparison to what Alexandra already mentioned. Freeze drying is extremely efficient in removing the water, but keeping the sensorial acceptance towards the consumer. It was one of the highest aim when we start with the freeze drying. And the acceptance or the feedback that we have received from the consumer, from the panelist, was great. They are keeping the flavor, keeping the texture, the color, the smell, and that I think it's a great added value in terms of this dehydration method. Going further with the economical aspects, we don't have an industrial type of freeze dryer, but in terms of energy consumption and everything, we have the life cycle assessment in the next presentation. However, we consider that considering the days that we succeed to prolong or to extend the shelf life of those specific berries, definitely worth the investment. And I'm sure that over time it will be reimbursed in terms of money or profits, because the loss is reduced to minimum in terms of losing the berries. Of course, we have tested the edible coating followed by the freeze drying. Here we had important added value in terms of bioactives and antioxidant activity, which have increased. But in terms of microbiological issues, considering that using the freeze drying, we are reducing to the minimum the water level, for that specific criteria, we don't need to use the integrated approach of edible and freeze drying. But in terms of bioactives and antioxidant activity, for sure. And moreover, we have used the leaves coming from the olive trees, which is an important byproduct that should be reintegrated and supported in terms of circularity. And the same for the rosemary. And they were all edible solution, food grade solution being extracted in water. What we have done in terms of mixing, we have combined the osmotic dehydration followed by the freeze drying in terms of drying technologies as an integrated approach. Of course, we did not use in this specific experiment also the edible coatings. But we have proved that the combination of osmotic dehydration with the freeze drying have reduced the drying time of the freeze drying with a specific number of hours, which actually brings economic benefits in terms of energy and resource consumption. And this is actually a work in progress article that we are now supporting as the consortia. And I would be extremely happy to see it already submitted and, of course, published, because brings important results. Thank you so much.
Thank you.
Thank you. Hello, everyone. I'll try to be short so we can go for lunch. And because the previous discussion between NTUA and USAMEVE was more or less what I was going to present. So I was going to present the sustainability assessment of the overall process. Not all the three aspects, because I don't have enough time to go through environmental, social, and economic aspects. So I'll be focusing mostly on the environmental aspects, and the rest I'll also illustrate in the poster outside that was prepared by Dignity and KPAD. So the main questions that we tried to answer through the FRIETS value chain in terms of the different processes was in terms of pre-harvesting, what type of cultivation is better, open field or protected? In terms of extraction, which of these 5 different processes are more cost viable and environmentally friendly? A discussion between freeze drying versus pre-treatment with osmotic dehydration followed by freeze drying. And then all of these, how do they affect the overall cost of the dried berry? In terms of the environmental impact, we followed the life cycle assessment using the environmental footprint methods, the software, the CIMAPRO software, and the EcoInvent database. And all the data were handed to us by the FRIETS consortium, so we didn't have any issues with data collection. I'll go through the 3 different processes to discuss a bit the main results and the main findings. In terms of pre-harvesting, the main question was about trying to compare the open field cultivation and the protected cultivation. And the question that Nicholas had, another question that would make him a happy man at the beginning of the project, was if he could replace or complement the traditional open field cultivation with protected cultivation in order to have yield throughout the year without jeopardizing his profitability. And we compared the open field cultivation of raspberries and the protected cultivation of raspberries in Cyprus. These were the system boundaries that we examined. As you can see, raspberries purchased in the Netherlands and transported to Cyprus, planting, irrigation, and then harvest the berries with the different emissions. The inventory, the main differences between the open field and the protected cultivation. The protected cultivation obviously includes all the material required to create the greenhouse, but it has lower water consumption, lower pesticide and herbicide consumption, which also leads to lower emissions. Comparing the two processes, you can see that the protected cultivation has a significantly lower environmental impact despite the material used, and the significant benefit comes from the water savings achieved using the protected cultivation. Now, in terms of the more important aspects of the cost, the open field cultivation seems to have around 22 euros per kilogram overall cost, whereas the protected cultivation has an overall cost of 14 euros. These values are pretty high compared to the market price of the berry for European countries. However, in Cyprus, where the market price is higher than the rest of the Europe, being an isolated island with all the transportation expenses, etc. involved, the suggestion that we had from the Cypriot partners was that the value might be high, but this is competitive to the price that they're already paying for the raspberries, the imported raspberries to Cyprus. Going now to the next step, the extraction. We have examined 5 different extraction techniques, which are not all of them mentioned over there. So it's Soxhlet extraction, maceration extraction, ultrasound, microwave, and microwave-assisted ultrasound extraction, and 3 alternative solvents: water, pure acetone, and a mixture of acetone and water. This is the life cycle inventory for the extraction, where I picked the best case for each one of the 5 techniques: the Soxhlet, the maceration, and the ultrasound, microwave, and the combination of both, in olive leaves. So there are different leaves trialed and different methods throughout the project. I picked olive leaves to demonstrate today here. Again, the difference between the processes are in the time of processing. Some of them take up to 6 hours, and some of them take just 15 minutes. And also the difference in the yield. So this is the main differentiating factor between the different processes. We've calculated the results 2 ways. One, based on the mass of the dry leaves processed, which might lead to some misleading results, showing this maceration being the best technique. However, if we compare the environmental impact based on the actual benefits of the extraction, the grams of gallic acid equivalent, the actual phenolic content of the extract, the ultrasound, the microwave, and the microwave-assisted ultrasound extraction are the more environmentally friendly techniques. The difference between them in terms of environmental impact is minimal, so the decision would be made based on the actual characteristics of the phenolics rather than the environmental impact. And the same conclusions can be drawn from the costing, where the additional cost added to the process from those 3 techniques is almost identical, so it wouldn't affect the decisions for from the scaled up or the which technique will you use on the cost. You can pick any of those 3 with a similar additional cost, so it depends on the actual quality of the extracts. Now, in the last question, we have the dehydration techniques studied. Again, one specific case study presented here, where we wanted to compare the freeze drying with freeze drying using pre-treated berries using osmotic dehydration, the discussion as we had earlier. I'm not going to go through the details. Lavinia and Alexandra presented extensively the 2 options. The main difference, as Lavinia mentioned, is that the pre-treatment with osmotic dehydration reduces the requirements for the freeze dryer by 6 hours, although it has solvent requirements and additional energy usage. However, the reduction in the time of the freeze drying by 6 hours is significant enough to reduce the overall environmental impact. So we propose that using osmotic dehydrated berries for freeze drying leads to better environmental impact. The difference is significant, but not that significant to make that decision imminent. If you think that the quality from the freeze-dried only berries is better, then you can pick that option as well. The additional steps that we did in the FRIETS project in the overall integrated sustainability assessment was to assess the public acceptance of the final product, not in terms of the sensory characteristics, but more in terms of how much would the customer be willing to pay to buy the berry. Estimates the range for the market price of the final product, evaluate the economic feasibility of the scaled-up process, and perform a SWOT analysis of the new business model. But since we're all pretty hungry, all the details are on the corresponding poster outside for these remaining steps. So feel free to pass by the poster and have a look at it. There's also a 200-page deliverable that you will have to read at some point and ensure that everything is written down properly. Thank you very much. Yes, the buffet is over there. Any questions? No. Magda?
But now, by closing the session officially, since FRIETS as a project will end up to a final product, this is our expectation and this is what we would like to have at the end, and to go through the whole value chain of berries from the cultivation to the consumer. At this point, I would like to ask the opinion of the stakeholders that we have together with us, mainly Dorian from the side of the producer. What do you think about all these novelties, all these cultivation practices, everything that FRIETS studies regarding the cultivation? As a producer, do you think that all these techniques will be helpful for you, will support you, can assist the viability and sustainability of the primary sector? Let's try with this one. Για να ακούσουν οι online, για να ακούσουν οι online. Το πατά. I don't know. Take the cue.
All right. Better? Or?
It's for the online.
Okay. So yes, for sure, that we always worked with basic agriculture, and during the let's say the past, and also coming from a small island, and the introduction to especially precision agriculture, it's helping us a lot as well, and we can also have better yield as well in the cultivation, and also, let's say, also the finished product will be much of a better quality. Apart from that, also the waste that is going to be reduced with the post harvesting as well. It will help also financially, since we're not going to throw away as much berries, because we're going to also to sell more the low quality as well products.
So you don't miss any part of the production?
Sorry?
Case. So you don't miss any part of the production, and this is give you a margin?
Yes, sure. It will help us to to use all the production.
And so another question: which is the percentage of price go up on those products who use the technique methodologies that you can afford for the market? I mean, the price of the strawberries now is I don't know.
The price of the strawberries is always fluctuating as per volume of yield.
Okay.
So
how much the percentage up would be affordable? And the second question, can we use the second quality strawberries for those applications in order to have an alternative for those qualities? And how much of the total production is the percentage of those second quality strawberries?
okay, as percentages, I don't know exactly, but for sure, in the beginning of the season of the strawberries, we don't have much damages. But coming to the end, where especially you need to take as much yield as possible to recover the costs and make more profit. It's really important that because we also have higher level of waste. So in the last 2 months of production, the waste can be up to 30-40% because in the market the strawberries will not have a long shelf life. It can be only 1 or 2 days, which is not enough to put on the market and sell. So the waste, I think, it can be reduced by, let's say, from 30-40%. It can go down to 10% for sure.
Thank you, Dorian. And also from the side of the end user, the producer of the functional product and the dry berries, Rezos, what do you think about the novelties that fruits bring? It is something that potentially, because we talk about the scalability and about the possibility of companies to incorporate these techniques and produce these final products. Do you consider it's going to be something viable, something of interest?
Yes, of course, Resus Brands as an SME, I think that the outcomes of the FRIETS project are practical tools that we can directly apply to modernize our processes and maybe to enhance the value of the product we deliver to consumer. However, I think that our equipment should be extended, and we have to follow maybe the next call and the next funding for this scope, because we want to expand the equipment and to apply all these procedures with the outcomes of the FRIETS project, but we want funds for this.
So we can search for funding to
Yes.
the pilot showcase.
Exactly.
Great, thank you. Thank you very much. Thank you all. So now we can go for the lunch. And for the online participants, we are going to be back at 2 o'clock with the session of Alia's project.